Hi, everybody. Welcome back to Mars Day 2021. Thank you so much for joining us for another session. This is a really exciting panel session. We've got three panelists and me chatting today about science in space. It's actually the first of 4 panel sessions. So we've got science in space, technology in space, engineering in space, and maths in space. And each of those panels has got some real industry experts and world leaders to chat with you about their job and their career and what's exciting about it and what's coming up. And if you have questions for us, there's a Q&A button at the bottom of your screen. So feel free to type questions into the chat. We're going to chat. I'm going to give a sort of quick presentation to start with on the kind of science that I love to do. Then I'm going to have a chat with all the panelists, and I'm going to try and incorporate your questions. So please type questions into the chat as we go along. I'm going to introduce the panel in a moment. I guess I'm going to kind of start with my sort of 15 minutes of exciting science, or things that I think are exciting. And then I'm going to introduce the panel, and we're just going to have a kind of a general conversation. But I'm really excited. We've got a fantastic panel for you today. So let me just, here we go. Let's talk a bit about, a bit about what I think is exciting and what I do. So I'm a planetary scientist. I work at a university. And I'm going to talk about some of the science that I've been involved in and what I'm excited about being involved in the future. So in essence, kind of what my job is as a planetary scientist is to understand the impact of the sun on the planets. So in this, here we can see my screen, you can see that of the sun, and you can see some dates next to those pictures of the sun. And you can see the sun, it's really variable. It's not the same. It looks the same to us as we look up in the sky. If it's not cloudy, we should never look at the sun. But anyway, it looks very similar, but it's actually really changeable. And so this is sort of 11 years, and it's an image of the sun, sort of a characteristic image for each of those years. And you can see it's really quiet, and then it gets really active, and there's loads of things going on the sun, and then it sort of starts to get quiet again. And this is called the solar cycle. And we're really interested in this because the sun has a huge impact on the planets in our solar system, as I'll talk about in a moment. And so we really want to understand this interaction. And so what I really do is I'm looking at, I described this yesterday. I was talking to a bunch of scouts yesterday, and I told them that the sun burps, and they thought this was brilliant, but it kind of does. So bits of the solar surface kind of explode outwards. These are called coronal mass ejections, and they fly through the solar system and they can smash into the planets. And I want to know how they impact the planets. So on the right-hand side, you can see the Earth there in the middle, and that blue region around the Earth's magnetic field sort of protects us from the sun, if you like. So these explosions from the sun kind of get protected from the Earth by our shield most of the time, but sometimes we don't get completely protected. Sometimes it can have quite big impacts on the Earth. So this is a subject called space weather, and there are people, it's actually a job title, space weather forecaster. So for anyone that's interested in a career in space, imagine saying you're a space weather forecaster. It's a pretty cool job title. But the impacts it can have, it can do things like damage our power grids. It can affect our communication systems. It can damage our satellites. And there are satellites orbiting the Earth all the time that we rely on without even knowing it. And they can be impacted. Either the whole satellite can deorbit, or the instruments can be affected. And there are lots of different sort of aspects of our lives that can be impacted by space weather. The biggest event that ever happened was in the 1850s. It was called the Carrington event. And that was a pretty big deal. But back then, they weren't so dependent on technology, so it didn't really damage their society. But what we're thinking is, if another big event happens, what could happen to us? And so as space weather experts and forecasters, what they do is look at the sun, try and see what's coming our way, and try and work out how we can build systems on the Earth that are protected from space weather, basically. So a big space weather event, kind of bad for us, kind of fun if you live near the North or the South poles, magnetic poles, because you see the aurora. The aurora gets really bright. The northern lights, aurora borealis and aurora australis, the southern lights, get really bright during space weather events, and they expand further towards the equator. So if you're in Scotland, one of our panelists is in Scotland, and actually there was a recent report saying, look at the sky, that you might see aurora in Scotland. I think that was just a few days ago. The aurora can come all the way down there, and you can look at the night sky and see this beautiful sort of lights dancing in the sky. And that's probably the only good thing about space weather events, really, is that you get beautiful aurora. There are lots of reasons why we need to be careful of them. And actually, the other thing that I'm working on at the moment is understanding Mercury. That's sort of my real area of expertise, is trying to work out the impact of the sun on Mercury. And to kind of give you an idea, this is a movie taken from a satellite orbiting the Earth. And what you can see, there's a tiny dot about a third of the way up the screen on the left-hand side. You can just see it coming across the solar disk there. That's Mercury. So this is trying to give you a sense of scale for the fact that Mercury sort of sits in the sun's atmosphere in some sense. It's so close to the sun, a tiny rocky planet, super close to the sun. You can see the sun, you can see it sort of looks like different colors there. We're looking in different wavelengths of light, and that's picking out different features of the solar surface. And you can still see there's sort of Mercury as this really tiny dot right at the bottom of the screen there, passing across. So you can see Mercury going across the sun there. So tiny planet close to the sun. And you might be asking, why do we care about Mercury? It's a rocky planet. You know, if I ask a bunch of kids what their favorite planet is, no one says Mercury. I think my job in life is to change that. But the reason I want everyone to be excited about Mercury is actually, you know, as a body, as a planet close to our parent star, it's really interesting because as we look and we find planets orbiting other stars, which we're starting to do, we're finding exoplanets, planets orbiting other stars elsewhere in the universe. When you look up at the night sky and you see stars, many of those stars probably have planets orbiting them. A lot of the planets we've seen identified so far are very close to their star, very close to their parent star, just like Mercury is very close to the sun. Now, there's lots of reasons for this. Probably the way that we search for them means we're more likely to find planets close to their star. But still, if we want to understand them, how they evolve, what they look like, then it's important that we understand Mercury, the similar planet in our own solar system. I'm really interested in also space weather on Mercury. So trying to understand the impact of the sun on the planet, but also using some properties of the sun to tell us about the planet. So in this little movie, what you're going to see is a little spacecraft coming over, some X-rays coming off the sun, as they do all the time, hitting the surface of the planet Mercury and causing the surface to give off X-rays. And we pick up those X-rays, and they're like a fingerprint. They tell us what the atom was that gave off that X-ray. And so we collect all these X-rays coming off of Mercury's surface. We build a picture of what Mercury is made of. So we really want to understand what Mercury is made of. It's amazing to me that we don't necessarily know the answer to this. One of our planets in our solar system, not that far away, we still don't really understand exactly what the composition of Mercury is. So that's a really important open question. And I'm interested in this because I work on a mission called Bepi Colombo. It's a joint mission between the European Space Agency and the Japanese Space Agency. And it's on its way to Mercury right now. So I was lucky enough to go and see it launch in South America. Went to the European Space Agency launch site in Kourou, in French Guiana. And I watched this spacecraft launch, which is quite nerve-wracking because it had an instrument that we built on board, which is called the Mercury Imaging X-ray Spectrometer. We call it MIX. And it's that X-ray instrument that's going to look at X-rays coming off the surface of Mercury and tell us what Mercury is made of. So I'm super excited about this mission. It's going to get there in 2025. So it takes 7 years to get to Mercury. It's a complicated journey. But when it gets there, it's going to discover so much about Mercury and its environment. I told you it will tell us about what the surface of Mercury is made of. We're also really interested in impact craters. And for all of you kids out there, this is a cool science experiment that you can do. What I've done here is I've got layers of colored powder, really thin layers done with a sieve in a box. And I'm going to drop in an impactor as though I was forming a crater. And you can see that as I did that, as that thing landed, just like forming the craters you can see on the surface of the planet on the picture on the left-hand side, you can see some of that yellow stuff kind of got kicked up as my impactor hit the surface and formed these rays, this characteristic pattern that come away from that crater site. And you can see some of those in the picture I've got on the left-hand side there of Mercury. We want to be able to look at what those rays are because they contain material that have come from under the surface of the planet. So we can do lots of exciting things by looking at things like impact craters with our instruments. And we can also look at the aurora at Mercury. So I mentioned the aurora at the Earth, giving us these bright lights in the sky that we see due to the interaction with the sun. Same thing happens at Mercury. It has its own little magnetic field. It's very close to the sun. So it sees that space weather event, that Carrington event, the worst possible space weather event that we've ever seen at the Earth. We see that at Mercury every day. And so that's why I really want to study Mercury, because I want to understand the physics behind what causes these big space weather events. And to do that, going to Mercury and seeing the big events is really important. And the aurora that I mentioned, at the Earth, we can see it with our eyes. In Mercury, we see it in X-rays. So we only discovered this a few years ago. Just so happened that we built an instrument that was going to Mercury to look at X-rays. So this is a great thing that happened by chance. Now we can use that instrument not just to tell us about the surface of Mercury, but also about the aurora at Mercury. So this is an example of how sometimes when we design missions, science changes in the meantime, and we have to adapt what we're trying to do. The other thing that I want to briefly mention, I'm sure this is going to come up a lot more actually, is the things we can do from space looking at the Earth, because I love looking at the other planets in the solar system, but there's so much that we can do using Earth observation satellites. I'm going to talk to one of our panelists a bit about that, small satellites and what we can do with them orbiting the Earth in a moment. But here's a few examples. We can monitor the rainforest, illegal fishing. We can look at disaster management. We talked a bit to Jeremy Curtis from the UK Space Agency a few minutes ago about disaster management. We can look at sea surface temperatures and monitor climate change. So more and more, we're looking down back at the Earth from space and this is helping us to sort of preserve the planet that we see. The last thing I'm going to mention is another Earth observation project, but actually the one that I'm probably most proud of, which is not planetary science in its traditional sense. This was an application of Earth observation data. I became really interested in finding all the mountains on the Earth's surface because I wanted to climb as many mountains in South America as I could, and I wanted to know where they were. And so I got some data taken from the space shuttle of the Earth's surface, altitude data of the Earth's surface. And there's a map of it on the right-hand side. You can see there where the color is elevation. So you can see the black's the sea and the red is the Andes Mountains. And there's 1.6 billion data points in that map. So lots and lots and lots of data. And we have a supercomputer at the university. And I wrote some computer code to find all the mountains in South America and sort of make an objective list, because the only list that existed at the point at which I wrote this code was this fantastic Scottish guy who got a map and a pencil, and he marked on the position of all the mountains in South America. And he actually did a brilliant job, but it's easy to be more accurate if you have data in a supercomputer. So I made a list of mountains in South America. There are 1,142 mountains above 5,000 meters. I was trying to climb as many of the 6,000 meter mountains as I could. But as I looked at the list, I realized there were dozens of mountains on my list that had no name, that had never been climbed before. And so what do you do when you find a load of mountains that no one's ever climbed before? You go to South America and you climb as many as you can. So since then, this is just a few years ago when we made the list, we've been heading off to the mountains to climb these unnamed mountains. And this is sort of where exploration meets science, I guess, because no one's climbed them before. So I have no idea how to climb them, what I'm going to find. If disaster strikes, there's no one there. There's no porters to carry my luggage for me. There's no map with a little route that tells me how to climb the mountain. It's all about sort of reacting to what you find when you get there. And that's, for me, that's sort of real fun of mountaineering. So the reason I want to highlight this project is because this sort of, for me, and the reason it's one of my favorites is this is bringing together mountaineering, which is a huge part of my life, and space science, which is another huge part together. And that's what made this sort of project that I did so rewarding. Just to wrap up then, I've been climbing in the mountains for a few months, and I came down to a small village called Fiambala in Argentina. They have free public Wi-Fi in Fiambala, by the way, if you ever find yourself there. And I opened up my laptop and thousands of emails poured into my laptop. And one of them was from the BBC saying, do you want to be an astronaut? I was like, huh. So I replied and said, yeah, I want to be an astronaut. And so, cut a long story short, found myself on a BBC television series. I'm the one in the beanie, by the way, so you can spot me, shorter hair back then. And we were going to do astronaut selection and sort of find out, what are you looking for when you're looking for astronauts? And so these people, from the thousands that applied, they picked pilots and doctors and scientists to sort of take part in astronaut selection. And that was really interesting just to learn what they're looking for. I thought they were looking for the smartest people on the planet who are also Olympic athletes, and the best at everything. And actually, turns out that, okay, you have to be fit and healthy and it's important to be good at your job. What else is important to do though? Things like get along with other people, be a leader, be a communicator. If you're going to space at the moment, you're going to go to the International Space Station, be stuck on a small space with a group of people who you probably don't know that well. So getting along with people turns out to be one of the key things they're looking for, as well as making good decisions under pressure, of course, which is why people like pilots and doctors are really good choices, and mountaineers too. Okay, so there's the brief sort of history of a few things that I'm interested and excited by at the moment. I'm going to stop sharing my screen now. If you have questions for me or for anyone else, then feel free to pop them in the chat, and we'll get to those a little bit later. I'm going to bring in now the rest of my lovely panel for this session. So we have 3 people on the panel. We have Eleanor, we have Hina, and we have Caroline. So I'm going to start by just asking you to introduce yourselves and tell us a little bit about what your job is and what you do. So maybe we'll start with Caroline.
I will take myself off mute. Hi, everybody, and thanks very much, Susie and the team, for inviting me to join this fantastic event today. So my name is Caroline Smith. I work at the Natural History Museum in London, although I'm not there today. I'm in my kitchen at home, where I've been working for the last year or so. So I'm the head of Earth Sciences collections at the museum. So I'm the head curator in the Earth Sciences department. We have about 10.5 million specimens in our department collections, ranging from dinosaurs to gemstones, meteorites to fossil fish and fossil seashells. So if it's a stone or a bone, we've got it in our collection. And I manage a team of about 30 curators who are all specialists in their field, and they look after those collections, make them available for exhibitions, but also as well for scientific research. So we have a very active scientific research program at the museum. So we're not just a museum of stuffed animals and things in cases. We've actually got about 350 scientists working at the museum on collections in the museum, bringing new material in. And so when I'm not doing my sort of curation management stuff, I'm a planetary scientist as well. I studied meteorites for my PhD. I started off doing geology, so many planetary sciences start off doing earth sciences, and then we go out into space. And for the last few years, I've been working with NASA and ESA on various planning for Mars missions. And you can see I've got my Mars 2020 t-shirt on. So I'm also very privileged to be a member of the Mars 2020 science team. And I'm working with an instrument called Sherlock, which I can tell you a bit about later if you're interested. And I'm also working with NASA and ESA. And this is really the thing that really excites me and sort of links my research and my sort of curation job, is that we're making the plans now for how we're going to curate and make accessible the amazing rocks that Perseverance is going to be actually collecting on Mars. And then those rocks we hope will come back to Earth in about 10 years, and they will be available to study by scientists all around the world. So there's probably many of you who are on this call now who maybe are a little bit younger. You're going to be the people studying these amazing rocks when they come back from Mars in about 10 years time, and do those research in years to come.
Brilliant. Thank you so much. I've got a question for you, actually, which we've been asked a lot today already, which is about the process of bringing things back from Mars. And so people sort of maybe thought in their minds, Perseverance is going to go grab some rocks, bring them back, but it's not quite as easy as that, is it?
No, it's very complicated. It will be probably the most complicated mission, certainly since the Apollo missions for the first humans to the moon. So no, it's a multi-step process, and there's going to be a number of things sent to Mars to be able to collect these rocks. So there'll be something called the Sample Fetch rover. So that's actually being designed in the UK. And I think is due to be built by I forgot the name of them, Airbus, sorry. And that will actually be a very nimble, very quick rover that will be able to go and find the samples that Perseverance has, and then bring them back to something which is then going to launch them off Mars. And then there's another satellite on Mars's orbit waiting for that thing. It's going to catch. So it's very, very complicated, lots of steps. And that's actually one of the things that's really cool. So NASA and ESA have partnered to do, it's called the Mars Sample Return Campaign, because it's multiple missions over many years. And so it's a really great way of sort of cooperation between NASA and ESA, and really combining the best expertise and experience of those two different organizations. So it's very, very complicated, but we're at the right time now. We've got the engineering capability to do this. And now we're just, as I said, making the plans to how we're going to look after these samples when they come back from Mars.
I'm going to ask you more about that later, actually, because I'm really interested in the sort of aspects of what do you do with them when you get them back. But I'm going to hold my curiosity for a moment, and we're going to move to Hina. So Hina, I'd really love to hear a bit more about your job, what you do, what excites you about your career.
Thanks very much, Susie. Yeah, so I mean, it's fantastic to be part of this day and to kind of get to talk about what we do in here in Scotland, where I'm based at the moment, and kind of in this area of exploration and discovery and kind of technology. So I work at a company called Spire Global, and we are a data analytics company that launches small satellites into what is called low Earth orbit, and that's kind of the orbit of just around the kind of International Space Centre, or just a little bit higher than that. So really small satellites, which are the size of a loaf of bread, a bottle of wine, really that big. If it could fit on my table if I was somewhere exciting that I could show you. And really these satellites are launched regularly every kind of 3 to 4 months in timelines. And we have over 100 satellites in orbit. And what they're doing is that they are constantly looking at what is happening both out in space, but primarily what is happening here down on Earth. So Susie, you showed a fantastic picture, which I might borrow at some point, of the Earth with all of the different aspects that you can use satellite data and information to tell you about what's going on our planet, soil moisture, rainforest, sea ice, weather patterns. And that's what our small satellites do. And my job in that is to work with organizations, universities, but also governments and kind of public areas who have a need to have these types of data. So, climate change obviously is a really important and significant issue that we're all dealing with, and so many people are intrinsically involved in what needs to happen. And so the data that we can collect from our very small satellites quite quickly can really inform and give a really interesting outlook on how that environment is changing on a day-to-day basis. And the beauty of what I do is that it makes me use my background, which is space science, very similar to what you've done, Susie, in the kind of beginning of my life, and really take that knowledge and say that how is that now impacting people on a day-to-day level? How can I use my understanding of our Earth environment from a space perspective and really add value into the kind of world that we live in today. And small satellites, like I say, they're very small, so we're launching these things every few weeks. And then, although there are many of them, because of the orbit that they're in, they actually only last for maybe 2 or 3 years, because they automatically kind of degrade, the orbits kind of deplete, and then they burn up in the atmosphere. And because they're so small, they just disintegrate. There's nothing on them that needs to either be returned or that will cause the issues with space junk. So yeah, no, it's really exciting to be part of this. And I think there are so many different areas within the space community and environment that people can get involved in. Young people who I've just heard from Caroline, who started in geology, geography, environmental work, and then work in an area of the space industry. So I think there's plenty of opportunities, and to talk about that as we go through this morning.
I just think people are going to be amazed that you're launching satellites the size of a loaf of bread. Like, amazing that you can do things with a satellite that size. It's just fantastic. And I think my question for you is, you said that there are lots of them up there and you launch them every few weeks. So tell us a bit about, do you launch them one at a time? Do you launch them in big groups? How does that work?
So you mentioned obviously that you went to French Guiana when you watched the launch of Bepi Colombo. Now Bepi Colombo is a significantly, it's a significant piece of kit. It's a large satellite, and there's lots of different payloads and technologies on it. And really, that takes quite a feat to get something like that into orbit. But these rockets, which are being used to launch these satellites, always have a bit of spare capacity. So there's always a bit of space, which is kind of not really being used, because the main payload takes up the majority of it. But then there's these pockets of areas that can be essentially sold a kind of ride share. So basically, you're piggybacking onto these things. So what we do, and many small satellite companies do, is that we buy this small space, and really we launch them in batches of 4 or 8, depending on the availability on the from the primary payload mission that these rockets have on capacity. And because satellites, even on the larger scale, there are rockets being launched mostly, some place in the world every few months. SpaceX is launching, you've got the Ariane launches, the Vega launches. So we don't really care what the primary payload is. We just want to have a little bit of space, and that's what we do. So we ride share and we piggyback on to what is a primary payload, and then just pay for that small element, and then just get deployed when we get into space.
I love this idea of like hitchhiking your way into space. I love it. I think it's fantastic. Exactly. Super interesting. Great. Thanks, Hina. So Eleanor, over to you now. Maybe you can tell us a bit about what your job is. I'm excited to hear more about it.
Yeah, thank you so much for this opportunity. This is a wonderful, wonderful chat. So I am a postdoctoral research associate, which means that I've completed my PhD. Can tell by my accent, I didn't do it here. I'm Canadian, so I did my PhD back in Canada, and I came over here to the UK into the Open University in Milton Keynes to work with the group who are involved with the ExoMars 2020 rover mission, so the Rosalind Franklin rover. So my job right now is looking at the geology and the geomorphology of the landing site. So what does the landing site look like? It's behind me here in a bit of a digital elevation model. Nice. And it's flipped the wrong way, but that's okay. And so I'm really interested in understanding what this surface behind me looks like. Is there a lot of sand? Are there features on the ground that are going to make it hard for the rover to move? Are there craters or little depressions that the rover could get stuck in if it were to sort of traverse in that direction? So I use high resolution imagery from the HiRISE instrument, and that's just a really spectacular camera that's in orbit of Mars right now, and it takes really, really crisp pictures of the Martian surface. And I take that and I put it into my computer program, and I look on those images for so many things: landforms and bed forms, sand and craters. And I'm really interested in how all of that is going to affect the mission. I'm a geographer and a geologist by training, and so I was able to take what I learned in my studies of Earth and apply them to Mars. Earth and Mars are not really that different when you get down to the brass tacks, and so it's great to take what we know about certain systems on Earth and apply them to Mars. And so that's what I do, and I'm also part of the PanCam camera team for the rover. So a really excellent camera bench on the Rosalind Franklin rover that's going to take some pretty spectacular photos of Oxyoplanum, the landing site, once we get there. And my job, once the rover lands and those pictures start to come back to Earth, is to help the teams decide where to go. So how to get somewhere with making sure that the rover stays safe. And on that traverse, also looking at interesting rocks or interesting features to tell us a little bit more about Martian history. So that's what I do.
Fantastic. I have so many questions for all of you. Eleanor, I'm just going to ask you briefly, when people think about rovers on Mars and it's going to be there for a long time, I think they, might think, oh, well, it can get quite a long way. If I got in my car and drove for a few years, I could probably cover quite a distance. I don't think that's quite the case for Mars rovers, though. So how far do you think, would you be planning on going roughly in let's say, a month or in a few months of Earth time?
Yeah. That's a great question. It's a very, very slow process on Mars. We want to make sure that we're being as careful as possible. There's no one to call if your rover gets stuck. Your engineers and your scientists back on Earth spend long, sleepless nights trying to maneuver rovers so that they are the safest as possible. I think during the nominal mission, which is the mission that we've signed up for, we're only going to be able to go a couple of kilometers. So if you were to go out, this afternoon for a nice walk, you might cover 2 or 3 kilometers in maybe an hour, depending on how quickly you walk. That is about as far as we'd be able to go in a month, and maybe even less. It really depends on where we land and what kind of terrain we land in. You think if it's somewhere flat, you and I might be able to, walk 2 or 3 kilometers in an hour. But if we all of a sudden saw, a hill that sort of goes straight up, we might only get a couple 100 meters up that hill in an hour or so. So it really depends on where we land, but we're not going to be going super far. It's a very slow, very methodical process, and we've got to make the most out of where we go. So
yeah, absolutely. Fantastic. Caroline, I want to throw the conversation back to you again, actually, and talk a bit about meteorites, because you mentioned meteorites and the huge meteorite collection that's curated at the museum. And I want to know a bit about the meteorites and why. So we get meteorites from Mars, and when we find them, and you probably have a lot of them, maybe you can tell us a bit about those. But why is it important to do sample return from Mars? What can we do with the sample return that we can't do just with a meteorite that landed on the Earth?
Okay, yeah, that's a great question. And actually, we do have a very good collection of Martian meteorites. It's one of the best ones in the world, actually. Excuse me. So Martian meteorites are great. I study Martian meteorites. They've given us a huge amount of information about Mars, which we compare with the data, that Eleanor works on, from the remote sensing, and actually sort of do a bit of ground truthing. But what's a bit, disappointing, that's not the right term. The thing with Martian meteorites is they're all igneous rocks. They're all volcanic rocks. And in many ways are very similar to the types of rocks we get on Earth called basalts, which are ubiquitous on Earth. They're also ubiquitous on Mars. So the Giant's Causeway in County Antrim in Northern Ireland, that's made of basalt. That's a very famous. So if you can sort of picture that in your mind, these dark volcanic rocks. Now, as I said, they're very interesting. I like those types of rocks myself, to be honest. But if you are looking, for example, for ancient signs of life on Mars, and there is increasing evidence to suggest that early in Mars's history, maybe about 4 billion years ago, it had a nice, warm, wet environment, exactly the sort of thing where you would expect life to start. And in fact, much more conducive to life starting on early Mars than the early Earth, actually. So if you were looking for the fossil signs of that life, so certain chemistry, certain textures, you're wanting to look in sedimentary rocks, because that's where you find evidence of fossils on Earth. You don't get fossil life in igneous rocks, because things don't live in igneous rocks. Well, they can live afterwards, but they don't sort of form there. So really we want to look at sedimentary rocks. Now, we don't have any Martian sedimentary meteorites, and there's probably various reasons for that. So that's why we want to go to somewhere that looks very interesting. It has the right type of features, the right landforms, as Ellen was talking about with Oxyoplanum. The Mars 2020 mission has gone to a different place. It's gone to a place called the ESERO crater. So this was a large crater that had water in it for a long time. There's also rivers flowing in and out of that crater. So all of the right sort of rock types are there to really sort of, if there was life, we should find evidence of it stored or sort of trapped within that rock type. So we need to be able to collect those rocks using the Perseverance rover, and the Perseverance rover's got an amazing set of different instruments, different scientific payload on it. So we'll look for those interesting rocks, look for the interesting textures, features, chemistry that could be indicative of past life, collect those rocks, and then bring them back, and then really get to study them properly in the labs on Earth. So that's why we need Mars sample return, to get the right rocks back to really answer that question of, was there ever life on Mars?
Thank you. That's a brilliant answer. Thank you. So I actually didn't know the answer to that. So thank you for that. Brilliant. Hina, I'm going to throw over to you and ask a bit about some of the exciting things that are going on with the space industry at the moment. So we talked a little bit with Jeremy Curtis from the UK Space Agency earlier, and he was telling us about launch sites from the UK. And so I wanted to ask you what your thoughts are about launching from the UK and what opportunities that might open up.
Yeah, no, exactly. And it's a very, very exciting time within the kind of space industry. So obviously we've got, academic work, which is ongoing and absolutely fundamental to our understanding and exploration of the kind of universe and the planet that we live on. But also on the commercial side, where, we talked about, looking at how the data from these satellites can be used to help us make decisions and help us understand our environment, to make it a better place to live and give us information to for technology or for navigation or for security, and all these things that are very important. On the launch side, obviously, as I said, generally the way we are doing things at the moment is that we kind of piggyback onto these large rockets, which can only be launched in very specific areas, because as you can imagine, they're large and there's a lot of security issues, but also in terms of the space, you can't be launching these rockets from populated areas, and they have to be over water and things like that to maintain environmental and other issues. What we're looking at here from the UK, and it's been talked about for some time, is looking at launch sites for the UK. Now, we're not looking at something in the range of Cape Canaveral. We're going to have this massive, SpaceX type rocket, which is going to go off from either from the north of Scotland or from the south of England. What we're talking about is the capability to launch what I've talked about, these small satellites. And because they're so small, you don't really need a massive rocket to get these things into orbit. There's talk of even just using just a slightly larger airplane from a horizontal launch site, so it would take off like a normal aircraft, and you would have your payload, the satellite, attached to the bottom of your aircraft, and it would go into a kind of suborbital or orbital inclination, and then you would deploy your satellite. Because again, we're not going to other planets; we're just going to around a few hundred kilometers up into the sky. So these sorts of things are actually mean that it can be quite accessible from a UK perspective. And there are a number of launch sites which have been identified here in Scotland, but also in Wales and the south of England. And it's really to support the industry to be able to get their assets into space that will then provide us with this data. So the Shetland, there's the rocket sites up in Shetland which are being tested, and there are companies here in the UK who are developing the rocket capability as well. So absolutely, it's a really exciting time. From a perspective of a satellite company, what it means is you travel to French Guiana. It's a world away. It took many days. It's quite difficult to get to. We're building our satellites here in Glasgow. We can then get our satellites built in Glasgow and then essentially just, transport it by vehicle to somewhere in the UK, then that is a fantastic opportunity, because it reduces the time in able to get things to launch. It also reduces the risk, because it means you're not having to package and then deal with some of our instruments are quite sensitive, so you don't want to jiggle them around too much. You've got to test obviously for the launch capability, but you don't want to be handling things unnecessarily, and transportation can be quite difficult. But also you don't have to deal with kind of customs and international regulatory issues. If these conditions can be dealt with within the UK borders, then satellites that are built here in the UK can be launched from the UK and therefore provide assets for everybody, but you don't have to deal with international customs and constraints within that environment. So it really gives us the opportunity, and we've talked already, with the panel, where instrumentation is being built here in the UK. We have the expertise and the skills to build this technology here. That technology can then be put on a satellite that Spire are doing or other people are doing, and we can get that into a satellite. It's called a satellite bus, so a satellite system, and then we ship it up the road to somewhere like Shetland or Cornwall, put it on a rocket, and then we get that thing in orbit. All of a sudden, that timeline could be, at the moment could be, a year or 18 months. That reduces down to a matter of, single months, 6 months or 8 months, or whatever. So it really kind of, it's a turnkey opportunity for us to open that door into providing that information much, much more quickly. And, again, just talking about that, if you think about your mobile phone technology, how quickly that changes. If you can imagine then having that capability being put into a satellite and then used in orbit, then all of a sudden you're really making use of the cutting edge environment technologies that you can use, rather than waiting 10, 15 years to then get something in orbit and then get it to where it needs to be. So we're really looking to leverage all of the exciting technological advancements that we have and get that into something which we can then use to monitor our planet.
Fantastic. And actually, for all of you thinking about the space industry, a lot of us think about working for the agencies, UK Space Agency, European Space Agency, NASA. Here we've got Hina working for a private satellite company. We've got Caroline working for a museum. You know, there's so many opportunities out there in the industry that aren't just related to the agencies. And sort of I encourage you to think a bit more about that. Eleanor, I've got a question in the chat. So somebody asked about how long it takes for communications to get to Earth from Bepi Colombo. The answer to that is it depends where Bepi Colombo is relative to the Earth at the time, but a few tens of minutes is the answer. But I want to kind of throw this to you in terms of driving Mars rovers, because a few of us have attempted to drive Mars rovers at the Mars Rover Lab in Stevenage. Some of us were terrible, but at least the thing was responding in real time to what I was trying to get it to do. Okay, it was pretty slow. It wasn't doing much, but, you know, I could see it. And it was receiving my signal quite quickly. Tell us a little bit about driving Mars rovers on Mars, because presumably this time delay has an impact.
Yes, it does. So the time delay is anywhere between, like 11 to 14 or 15 minutes. So you send a signal, it takes 11 to 15 minutes to get there. Then it takes time to execute. And then you don't know if the rover has done what you want it to do for another 10 to 15 minutes after that. So just telling the rover to, move, forward 5 meters, you're going to be, the whole thing is going to take about 45 minutes to an hour, depending on where you are, where the Earth is, where Mars is, and where we are in the orbit. So it takes a lot of careful planning, as I was mentioning before, to make sure that you're telling the rover to move 5 meters, that it's not all of a sudden going to pitch into a small depression, and then you're going to spend the next 6 months trying to get it out. So it's very nerve-wracking, because you've done your homework, you've done the best you can, you've told the rover what to do, and now you just have to sit back and wait. And that's a really scary part of the science for all of us, because we want to know right now. We're so used to opening up the internet and it being right there, or making a phone call and someone being right there, and now we just have to sort of gotta wait a little bit. So that's really difficult when trying to move the rover. And then once it moves successfully, a couple meters ahead, now you've got to take a whole new set of measurements and take new pictures and look around, and you've got to plan out how you're going to move the rover the next 5 meters. So every little piece of Mars that's gained by rovers moving takes a really long time to come to fruition. So just sitting there and waiting for about an hour for everything to execute, but there is a lot of work that goes in, hours and hours and hours that go into making sure that rover's track forward is safe and successessul. So
interesting. Yeah. And actually, if something goes wrong, you can't just phone the AA to come pick you up. You're in trouble. So but lots of responsibility on you guys to make sure you get it right, for sure.
Yeah. And there's a lot of the Martian surface that we are not 100% on. The Curiosity rover was stuck in something that the scientists called Purgatory Dune, or Purgatory Ripple, because it was stuck for 40 sols, or 40 Martian days. They didn't realize that what they were moving into was actually soft sand, because the pictures that they were getting suggested that it would take the weight of one of the rover wheels, when in fact it just sunk through. And so the engineers spent 40 sols, or 40 Martian days, trying to get it out. So even with the best planning, we still sometimes get to Mars and think, oh, we've got this covered, and then sand stops you in your tracks. So yeah.
So interesting. I've only got time for one more question. It's going to be to Caroline, because Caroline, I saw you talking to the Queen recently, which is highly exciting. We're an exalted company. And I want to know a bit about a meteorite that landed, I think, near Cirencester. So can you tell us a bit about that meteorite and why it's important, and how you found it and where it is now?
Well, so I have to say, I wasn't one of the people who went out hunting for it. I was able to stay back at base and do all of the paperwork so that they could go out and hunt for it. So it was actually the 28th of February, a large fireball, so a very, very bright shooting star, was witnessed over huge amounts of the UK, and actually over to France and Belgium and the Netherlands. People saw it there about 5 to 9 in the evening. So it was nice and dark, and it was actually quite a clear sky. So it was very, very well observed. And it dropped pieces of meteorite, which, as you say, were just north of Cirencester in Gloucestershire. And so we've collected a number of pieces of it, about 500 grams so far. And most of that is in the Natural History Museum. It's currently being curated by my team, who are working very hard on making sure it's all documented and it's being kept very carefully and very securely. Although I actually managed to get out of London on Monday, and I hand carried some pieces. I had to get special permission to travel, actually up to a colleague who met me in Carlisle, and she carried on to Glasgow. So the University of Glasgow are doing some urgent analyses that can only be done very quickly after the meteorite lands. So yeah, very exciting. It's a very unusual type of meteorite called a carbonaceous chondrite, and these are some of the first materials to form in our solar system. So very interesting from solar system history. But if I've got, can I just quickly show one thing, because it relates to a question. It relates to a question. So somebody asked a question about, did we send a meteorite back to Mars? We did. So we worked with NASA, and we have a small piece of one of our meteorites called Sire Al-Uhamir 008 or SAU-8, and that's been included on the Sherlock calibration target, and we got our first photo back yesterday of it. So we have a piece of Mars back on Mars sent by a NASA rover, but I can't actually share my screen to show you the picture, unfortunately, because it says host disabled participant screen.
So perhaps
so I can't show you the picture.
I think you can now, actually. Let's have see if you can.
Shall I see if I can do it now? Oh, there
yeah,
you go.
We want to see it. I think it's amazing. A piece of Mars broke off Mars, landed on the Earth. We found it. We put it on a mission. We've sent it back to Mars again.
Absolutely. So this is actually the Sherlock calibration target, and you can see there's a number of things there, and that's the piece of meteorite, right hand side in the middle. You can see the different texture of the rock there. But the other thing that's quite cool about this, and I realise we're probably out of time, I'm sorry everyone, but I think it's just really cool.
Go ahead.
And it relates to a question that was asked by a school who said, when, will we be sending humans to Mars? And yes, this is the ambition of certainly NASA and other space agencies. And so maybe as soon as the 2030s, but who knows? But you can see there's different materials on the left-hand side there. That's actually different types of material that would be used in the spacesuits that the astronauts who go to Mars would wear. And they've been sent on the Perseverance rover to actually see how those materials stand up to the harsh Martian environment, and will they actually be suitable for spacesuits for astronauts who will go and explore Mars in the future.
Wow, we're testing materials on this mission. Looking forwards. That's a great note to end on, actually.